Hello, testing. Good. And morning, guys. I hope you had a wonderful weekend, especially those who are in Houston. You made it safe. Okay, so this is your password. Make sure you install. I assume you already installed the program. I mean the exam, sorry. So this is your password. When you get to the start screen, just stop there until we set the timer, okay? We'll give you a minute or two. Let me see who's not at the start screen now. If you are not, okay. So wait a few more minutes. Okay, let me check again. If you are not at the stop screen, at the start screen, raise your hand up high so I can see it. 1, 2, 3, 4, 5. Okay. Okay, let's see who's not at the start screen again. Raise your hand up high, up high. 1, 2, 3, 4, 5. The same number. For those who are not at the start screen, when you do get to the start screen, can you please just give me the sign so I know who's not yet? Okay, the 5 people who raised their hands, if they are, once you get to the start screen, just give me the sign, okay? Okay, let me see now. Let's see how many are not at the stop screen, at the start, I'm sorry. Are you there yet? I'm sorry. I think no, you're not yet. Okay, can you raise your hand up high so I can give you a paper copy? Okay, 1, 2, 3, 4. Okay, so let me get you the paper copy then. Okay, everybody is ready at the start screen or has a copy? Shh. Everybody is ready to start the exam. Let me set the timer. There should be like 10 minutes. I think we need more than that. Not yet. And those who had the paper copy do not start yet. All right, go ahead and start. Good luck. Okay, everyone has submitted their answers, I assume. Let me set the timer, and then you could start working as a team. For those who take the paper exams, you could please bring it back to me. Thank you. All right. So now you could start working as a team. You have another 10 minutes. Guys, for question, thank you. Question number 7, you're gonna put the answer on the sheet, okay? The matching question. So skip the scratch paper for question number 7 and do it on the sheet, okay? Okay, so let's go through the questions. Okay, question number 1. Lipophilic drugs have higher log P, oil in water or octanol in water, value than hydrophilic drugs. Sure. Give you, I'm sorry, what? Yeah, I normally send you the results with the questions and answer. Didn't you receive that on ExamSoft, Exemplify? I also post it on Canvas, okay? It's okay. So when right after the class, actually, I go to the ExamSoft and release all your scores, including the questions, the answers, your answers. So you should see that. Make sure you are able to see that on ExamSoft, okay? Okay, good. Okay, so question number 1. Lipophilic drugs have a higher log P value than hydrophilic. We all know it's true, of course. We, scratch the cards. So remember how is log P, how P value is calculated? Right. What's this speaker in here? Which one goes on top? Oil and water, right? So that's why, if there's a leak in the sea, then oil always starts in the top. The same with the, what do you call this, denominator? Yeah? Numerator. And this one is, okay. Okay, so it's easier to memorize, right? The oil goes on top, water goes on bottom. So the same for the concentration of the drug, oil in water. So if you add a drug to this beaker, part of the drug will dissolve in the oil, another part will dissolve in the water. Now the concentration of the drug in the oil, if you divide it by that of the water, it will give you P, oil in water. This value actually ranges, in hundreds, but to make it easier for us to memorize, we take log that value, okay? So then you have ranges in like 1, 2, 3, 4, something that is easy to handle. Now, the higher the P, oil and water value, or the higher the log P value, it means it's more, oil or octanol. Octanol is a representative of the oil. It's more octanol or oil soluble, so it's more lipophilic. Got that, everyone? It's okay, sure. So if we go to this chart here, when you have equal amount, if the drug is distributed equally on both sides, then you have P equal 1, okay? Now, as the value increase, you get lipophilic, which is a typo. I know. Of course. Okay, fair enough, fair enough. Yeah, well, nice catch. See, I had this for like, I had this for like 2 years. You're the only one who got that, which is you guys are smart class, right? Okay, so yes, the lipophilic should go on the other side because normally it's positive going this way, right? Okay, okay, that's fine. So we'll make this a bonus question, okay? Nice catch. Yeah, see what happens when you argue and ask questions? You get more points. But back to the concept itself. Is it clear, guys? This is something you should know by heart because later on, anytime, we're not gonna even say lipophilic, hydrophilic. We're just gonna say this drug has a higher log B value. You should know by heart that it's a lipophilic, okay? You will also have to deal with this later on with pharmaceutics and pharmacokinetics. We're not gonna talk about lipophilicity, hydrophilicity. We're just gonna say high log B value, low log B value. And the way I like to memorize it, just like I explained it, is the oil goes in top always, whenever you mix two things, water and oil. So the numerator is the one that goes on the top, and the denominator on the bottom. So that's how I, try to memorize it. Now, if you, log p value is what we don't use p value, we use log p value because, like I said, values in hundreds, it's harder to memorize. But when we convert it to the log value, then we are talking about, numbers 10, 5, and so forth. Okay, so I know you had a question. Yes, ma'am. Right, so if you got this question right and you missed something else, so this would help you, this would substitute that. Okay, so the bonus question means that, all the other questions, the 9 questions, the 10 points will be spread over the 9 questions, okay? And then if you miss something, this question will come in and help you. But if you get 100% all the questions right, then I cannot use that for the next rat, for example, or the rats before. Make sense? Okay, right. Any other questions? Yes, sir. What do you think? Yes. Yeah, log b is not going to change anything. Yes, so the value and the log is just, correlated. Now, that's not the case if you say minus log b, but that's not, we won't worry about this for the p oil and water for the partition coefficient. We will see that in the, the association constant. So the pH or pKa is the minus log for the concentration, but we're not going to worry about that. So this one is straightforward. Log B or P, it's higher, means it's more lipophilic, lower hydrophilic. Got it? Yes, ma'am. Yeah, right. So one means that they are equally, the drug is equally distributed on both sides. So it's like in the middle. If you take log 1, what is log 1? 0, okay? Log 1 is 0. If you take the log value for this, it will be 0, okay? So if I say, a drug has partition coefficient P oil in water of 100, then you should know by yourself that it's lipophilic, okay? If I say it's 0.5 or 0.01 or anything below 1, then it's hydrophilic, okay? Make sense? Any questions on this? So I know there's a lot of concepts in today's material, so we'll break them into pieces, each one by itself, and then we'll see the applications, how we can use that together, okay? All right, questions before we move to the next one? Last call for questions? Okay. Okay, question number 2. What statement is most correct regarding the blood-brain barrier? Okay. Hydrophilic drugs pass through the blood-brain barrier more easily than hydrophobic drugs. Is this right or wrong? Wrong. Why is that? Which one? Blood-brain barrier has fatty tissues, right? And so hydrophilic are polarized or ionized, so it's hard to cross through the lipophilic layers. It should be the opposite. Hydrophobic drugs are actually easier to pass through the blood-brain barrier because blood-brain barrier are tight, thick, and fatty. It's actually a way to protect our brain and central nervous system, okay? It's not easy for any drug to pass through the blood-brain barrier to our brain, so we're lucky, okay? Unless we're designing a drug to actually act centrally in the brain, like we need to help with the anxiety or help somebody go to sleep, something like that. We'll see that in the applications, okay? Okay, so we all agree A is incorrect. Increasing polarity or size of a drug makes it easier for it to cross the blood-brain barrier. False. Why? First, it should not be polar, right? It should be less polar. It should be decreasing polarity. It should be more lipophilic, like we said, to cross the blood-brain barrier. Second, size also matters. Smaller molecules are able to cross blood-brain barrier better than larger molecules. For the same reason, the blood-brain barrier has tight cells, very tight to each other, lipophilic fatty tissues. So, okay. The blood capillaries supply the brain have less fatty barrier through which bloods can cross. You have already know it's wrong. Okay. Drugs should not act in the brain. Drugs that should not act in the brain are made more hydrophilic. What? Okay. So what advantage does this sentence give us? So if we need drug to act somewhere else, not in the brain, right? Because sometimes if drugs crosses the blood-brain barrier, they can cause some side effects, right? Okay. That's why some drugs will make you sleepy, because they cross the blood-brain barrier and interact with the receptors and make you sleepy. So our goal is to prevent that from happening. So what do we do with the drug? When we design it, we make it more hydrophilic. Got it? Okay, any questions on this so far? Sure? You looks like you have a question. Are you sure? No, okay. All right. Number 3, drugs with smaller particle size have faster dissolution rate than drugs with larger particle size. True. Can you give me an example in real life where small particles dissolve faster than large particles? Salt, the coarse salts, or harsh, what do you call it? Coarse, salts that are not like large, they're not small particles, then takes longer. The same with the sugar, the sugar cubes, they take longer time to dissolve, right? But if you have a ground sugar, faster. This is a technique to actually facilitate, the absorption of the drug. Okay, so normally drugs that are poorly soluble in water, we actually try to break them into smaller, pieces, such that they actually dissolve faster. Okay, it's also a technique when we have, drugs given as tablets versus solution. Which one do you think is fastly absorbed? Solution. So for example, Advil cap gel is faster than Advil tablet. Okay, if you need something to act faster, you have a headache or pain, then the cap gel would actually act faster than if you take tablets. Make sense? Okay, you have a question.
Okay. Is it, other than just, it sounds like it could, that like is probably the case. What is going on here? I mean, I looked at this from the point of view of, well, a lot of times larger particle will have more, like the example of a multi-carbon molecule with polar things, is when we end up with an equivalent amount of carbon to polar ratio and it's large, do you end up with still a slower, or is it just a general?
This is actually an excellent question, because this brings me back to the next point I wanted to talk about, which is the crystal form. Now to answer your question, the level of the particle size here we're talking about is the powder versus tablets. But when we go to the level of the molecule, then when you go to the level of the molecules, then we care about the crystal form, the polymorphism crystal form. Now, at the level of the molecule, molecules can crystallize in different shapes, right? So if they crystallize in a way that they are, porous and, this oriented, then it's easier for water to get inside and dissolve it, right? But if they are crystallized in a form that are packed, right, it's going to be hard for them to dissolve. Okay, so that's a good point. Thank you for bringing this. So crystallization, does that answer your question? It's like, no. Okay. Okay. Yes.
I was thinking
Right. So when we talk about the particle here, we're not referring to the molecules level. We are talking about the, I guess, micro level, or like level of the powder compared to tablets. Okay. Yes. Yes. So just like we said with the example of the sugar and the powder, the sugar cubes versus the powder. So two factors affect the solution at the level of the particles. The smaller the particle size and the more grounded the tablets or the drug, then it's easier to dissolve. Second, the way it's crystallized. Okay. In fact, that's why you have, this is one of the factors that affect generic drugs, right? So you take a drug, they have exact same ingredients, right? Dosage and everything. One of them acts better than the other. Why is that? This is one of the reasons. It depends what source, how did they crystallize the drug? How is it manufactured? Okay. In fact, pharmaceutics and the way how drugs is manufactured is a whole branch of science that can highly impact how drugs can act. That's why you have sometimes generic or brand name, different actions, different pharmacological actions. Okay, even though they have the same ingredients. Just like if you give the same ingredients and recipe to two people and cook the same meal, right? So it's in the way they prepared things and the details in the ingredients itself. Okay, you get that, everyone? Crystallization plus particle size. Okay. Any questions about this so far? Okay, let's move to the next one. Which of the following properties is preferred for an orally administered drug? Hydrophilic, hydrophobic, we all know that it's a balance between both, none of the above. Do you know why do I need to have a balance? Why should there be a balance between lipophilic and hydrophilic? Yes, ma'am. Okay. Okay, excellent. So because there are two issues we need to address. First, the drug has to dissolve in the GI fluids. So it does need some hydrophilic properties, okay, to dissolve. And then besides dissolving, it should be able to cross the GIT wall, the gut wall, okay, the intestine. So and this is a fatty in nature, so it does need some lipophilicity. So when we say a balance, so what happens if it's too hydrophilic? Will it dissolve? Okay. Will it cross the gut? No. Okay, well, if it's too lipophilic, it's not going to dissolve in the first place. And even if you give it by IV, it's going to like precipitate in your blood, the plasma, because it's not going to dissolve in your plasma. Okay. So we need a balance. So when you say a balance, this is like a gray area. To be more specific, there is a range in numbers. So we look at log P value, and the ideal value is between two ranges. Can you guys remember them from Lipinski's rule? It should be below 5, roughly, but this is by Lipinski's rule, but there's advanced version of Lipinski's rule that says log P should be between, I'm sorry? Minus 0.4 and 5.6, thank you. So Lipinski is a smart guy who's been with Pfizer for 30 years, and they always struggled with how to design drugs that are orally active. So he decided to look at all the orally active, and by the way, when I say orally active means a drug can be given orally, okay? Some drugs cannot be given orally, like insulin has to be given by injection, right? Eye drops, they can only be taken topically. So there is a stress, I mean a big deal of making drugs to be taken orally because it's more convenient, okay? So he looked at all the drugs that are taken orally, and he looked at the common features among them, And he noticed that the number of hydrogen bond donor is below what, 10, acceptor is 5, or the opposite. I don't recall, but you guys have to recall it. Log P should be below 5, but then the advanced one was between -4 and 5.6. And what else? The number for tetramethyl bond should be below 10. Molecular weight should be below 500. So he found that there's a common features that characterizes these orally taken drugs, and he set his rule of 5, saying that for a drug to be oral, it should orally active. It should follow these rules. It cannot break more than 2 of these rules. Okay, so this is Lipinski's rule. Now, why do we care about drugs should be taken orally? Why is it a big deal? I mean, it's more convenient, right? Imagine if you have to take a drug by injection or topically or, whatever the form is. So orally drug is the preferred, okay? It's actually $1 billion business, because if you have a drug that's taken by injection and you make a drug that's taken orally, you win. Everybody's gonna want to take your drug, right? It's more convenient, right? Just like you eat something, you take a drug, that's it. And we will also talk about the frequency of how the drug is taken. It's another $1 billion business. Instead of taking a drug twice or 3 times, horrible. If you ever taken a drug, 2 or 3 times a day, it's just, annoying. But if you take it once a day, or even better, once a week or a month, then convenience. Patient then, you will see patient taking their drugs and not missing a dose. You have a question? No, no, I wouldn't memorize them. No, just I guess appreciate what they're really about. Why we need to know them. And okay, yeah, no memorization in my class. If you see something I ask you to memorize, you can argue with me that you said no memorization, right? And then I will, normally I attach a figure to any question, so you could actually use it. I believe as Google is alive, then you don't need to memorize anything, right? As long as you have your smartphones, the only thing you need to know is how to use that information, because information is there. I mean, you can find them in your, computer. I shouldn't say Google, because there is some authentic really sources. That's a big deal, guys. So you need to pay attention to where you get your resources from. Okay, there is some authentic software that you will learn about how to use. These are the only ones you should ever trust. Okay, I mean, Google is a nice man, but we're not gonna, trust him that much, especially when we deal with patients. Okay. Okay, so this answer your question. Anybody has a question about this so far? Any questions so far? Last call for a question. All right. Okay. Next ones. Drugs that are bound to fatty tissues or plasma protein are less able to diffuse into the surrounding tissue where receptors are located. We all know it's true, right? Why is that? Excellent. It's the free ones are the ones that are able to, dissolve in the plasma and cross to the receptors and reach the tissues receptors. Okay. So remember, we'll talk about this in the applications. Some drugs, they bind to the plasma protein like albumin, or to the red blood cells, or they bind to the fatty tissues. So these will stay away out of the plasma. So if they are not in the plasma, they are not going to actually be available to move, travel, and go to the receptor and bind. Okay. So these drugs can affect us in many ways. I don't want to waste too much time on this, because we'll have a whole application about that. One of them is for these drugs that are bound to these macromolecules, we have to give higher dose to counteract that. Plus, if we have another drug that competes for the same, plasma protein or red blood cell or fatty tissue, they can displace them, and then you will have a drug-drug interaction. Okay. And then I forgot the third one, but we'll visit it in the applications. So, any questions so far? Any questions? Okay, next one, number 6. What's the preferred method? Okay. And this one. Okay, the first one describes what? Pharmaceutics, right? Pharmaceutical phase, because drug, before it's absorbed, it has to disintegrate and release and dissolve. And then the second one describes what? Kinetic. What's the short acronym we use for absorption, distribution, whatever? ADME, okay. And then the last one, of course, pharmacodynamic. Any questions about this? Okay, next one. For a basic drug with a pKa value of 5.4, what form would be most dominant at plasma of 7.4? I know we all got the answer of, what is it? Anionized, everybody agree? Okay, so we will have an application and have you use the equation Henderson-Hasselbalch to calculate how much exactly. Now, you really don't have to do the math here. If you remember the table, it will help you summarize. If you actually, just find a way to fill one part of the table, just one cell in the table, then you could fill the others. So the first thing you start an exam, you just draw the table and have it in front of you. You could just, use it. You will have to use Henderson-Hasselbalch equation for other courses, in the pharmaceutics and in the pharmacokinetics. You will have questions where you have to calculate the percentage ionized and unionized. But for me, I just want to make sure that you know what's the most dominant form. That's it. Okay. Okay. So when do you have the percentage ionized and unionized equal to each other? 50% of each. When do you have that? At what would be the pH and pKa value? When they are equal, not when they are equal. Okay. In fact, think of the definition of the pKa as the value. It's the pH value when 50% of the drug is ionized and 50% is unionized. Okay, this is how I like to think about it. The pKa is simply the pH at which 50% of the drug is ionized and the other 50 is unionized. If you understand that, then immediately you will know that, okay, so above pKa, it's going to be either ionized or unionized for an acid. Below, it's going to be ionized or unionized, depending on whether an acid or base, okay? All right, questions about this? Yes, John.
Okay. Which one of those did you say was the answer that will determine whether or not?
Okay, it's a base, pKa is 5.4, pH is higher, so it will be unionized. So answer C, the answer is C, okay? Any questions about this? Okay, number 9. The following structure is for a basic drug. We all know it's true. Now, what is the rule of thumb to differentiate between basic and acidic drug? So, carboxylate. If you see a carboxylate, which is a C-OOH, it's an acid, okay? If you see a nitrogen, it's a base. That's it. Very simple. In fact, these are the only ones you're ever gonna see, 99% of the cases, okay? Where carboxylate, it's an acid, nitrogen, it's a base, okay? What if you have both? We're not gonna worry about that, but conceptually, if you have both, then each one is gonna have a different value, pKa, and I will have to calculate the ionization for each one separately. And depending on the pH, then I will have part of the drug being ionized, another part unionized, and so forth. So you might have a drug that has more than one group at that certain pH, all of them are ionized. And you might have the same drug at different pH value where all of these groups are unionized. And you might have something in between. So, this is just extra information. I mean, just as additional. You don't have to worry about that. But just in case if you are, curious, because I know you are. So, you could actually try to see the percentage of ionization for each group in that drug and compare it with at different pHs and see whether it's soluble or not. Now, the good news is once you have one group that's ionized, then it will extremely increase the solubility of the drug. Okay, so right. Anyway, so any questions about how to know how to define a drug if it's an acid or a base? Yes. Yes. So acidic will have a carboxyl group. Basic will have nitrogen. And this is what I mean by carboxyl group. So something like this: aspirin, COOH. This is a carboxylic group. In fact, if you look here, we have acidic and we have nitrogen as basic. The other ones are neutral. We won't worry about. Yes, sir.
This question actually partly refers to the previous question.
Okay.
If you were to make that chart and instead you had PKB, would you flip the result?
Yes. Okay, so his question was, what if I'm using the PKB, not the PKA? So would your table would be exactly the opposite. Okay. Normally, the standard one is pKa, and that's one we're going to be using for an acid or a base. Okay, because it's easier and because they're related. If you know one of them, you know the other one. Okay, and for the purpose of this course, we're not really worried about how to calculate pKb and how is that affecting Henderson-Hasselbalch. For me, I just want you to appreciate the ionization at different pH, different pKa, and then be able to define whether a drug is going to be soluble or not, whether it's going to be able to cross the lipophilic membrane or not. Because why do we care about the ionization, guys? Because we can tell if it's water soluble or lipid soluble, right? If it's water soluble, it's gonna dissolve in the fluid of the stomach. If it's lipophilic, then it's gonna cross the gut wall. It's gonna cross the blood-brain barrier and all that. We'll see examples about that in the applications. Okay, questions? Questions? No questions? Move to the next one. Number 8, okay. Any questions before we go to number 10? Okay, so lipophilic drugs safer than hydrophilic for a pregnant woman. We all know it's false, but why? What is it about, special about, pregnant women or they can pass what? The placenta. So think of the placenta as the blood-brain barrier, okay? It has a lipophilic in nature. It's actually less lipophilic than blood-brain barrier, okay? And because you will see some examples where drugs can not pass the blood-brain barrier, but they are able to pass the placenta. But for simplicity, it's a lipophilic in nature, which means if you are worried about, the baby, then you want to give a drug that's what, lipophilic or hydrophilic? Hydrophilic. So this way you can be sure that it's not going to cross the placenta and reach to the baby. Okay, so this sentence is false. Questions? I know somebody wanted me to visit this question and explain why is it, but is it clear now, everyone? Did you have a question here? No? Did you have a question? Okay. Yes, ma'am. Okay, so placenta is lipophilic in nature, just like blood-brain barrier. Okay, so the same example with the blood-brain barrier, the placenta is lipophilic. So we will see in the applications that drugs that are more lipophilic, they can reach the patient and cause some harm. But those that are hydrophilic, they cannot pass the placenta. Yes, ma'am. Okay. Okay. That was like 20 years ago. I remember, I learned about that. I can't remember why is it. I'm sorry. Yeah, the positive and blood things. Yeah, thank you for for embarrassing me. Huh? They do? They oh yes. Yeah, so they do the test before and of course. Yeah. I mean, actually one of the reasons I don't like you guys to memorize things because I don't memorize them myself, okay? Seriously. I mean, yeah. What did you just say now? Anyway. Yeah, so I mean, no memorization. I like to understand concepts. Okay, so let's you have a question, yes. Say again. Oh, a drug that contains, that's a good question. Okay. So I would treat the sulfa, the S double bond O as a neutral, but if it has S double bond O and OH, then I would treat it as an acid. Okay. But that's rarely, we rarely will see drugs that has sulfa. Okay. So that's why I meant, like 99% of the drugs, it's going to be either, nitrogen or carboxylate. In fact, speaking of that, let's say 90% of the drugs are acid-base, 10% are not, okay? Out of this 90% that are acid-base, who do you think is the majority of drugs? Is it acid or base? Base, okay? So majority of drugs that are, could be acid or base are actually base. So let's say 80% are base, 10% acid, 10% none of the above or neutral, okay? So if you're not sure, you just want to guess, then just assume it's a base just in case. If you're not really, if you're not sure, okay? That's to be safe, then you could just assume the drug is a base because most of the time it has a nitrogen and you rarely see a carboxylate, except cases where like, the aspirin, okay? Okay, so I assume, wow, it took us an hour and 2 minutes. So I assume you need a break, right? So 5 minutes, is 5 minutes good, guys? Okay, no? 7? Sure, 7 minutes. 7 minutes break and come back at, let's say, you do the math. So Okay, so let's get started. So the first application talks about the journey of a drug that's orally taken because it's more, it has a broader steps than the case. What is that over there? Okay. So let's start with the first application. It talks about the journey that the drug goes through when it's taken orally. Okay. So I want you to illustrate, the pharmaceutical phase, pharmacokinetic phase, and the pharmacodynamic. Okay. And then identify the challenges that faces the drug when it's taken orally. Okay. Make sure you list all the possible challenges, and we'll talk about how we can address them. Okay. So let's see, 5 minutes on this question, maybe, because you studied the material over the weekend, right? Okay, so 5 minutes, sure. So it's 10:22, so maybe at 10:57, okay? And let me know if you have any questions. I'll be just walking. All right, 10:27, not 10:57. Guys, be prepared to, explain your answer here at the DocuCam, okay? Not trying to scare you, but just when I call for teams, they will come into the DocuCam and explain their answers. You guys need more time? Okay, 2 more minutes. Okay, so I assume you guys are ready. Good. Any volunteers? There we go, 2 teams. So we're gonna have you both do, but one after the other. Let's start with team number 11. Applause. And then you guys will go next, okay? Take your time. I'm sorry, yes. Yes, you're gonna go both actually together, A and B. Okay. But if you have A, that's fine. If you wanna do A, sure. You have both? Okay. So you're gonna do both, that's fine too. Right, so you're gonna, yes, the dark gun, please.
Okay, so we have the question is describe the journey an oral drug goes through, including the 3 phases of drug action. So we want to start with the first phase, which is the pharmaceutical phase, and this has to do with disintegrating the capsule or the pill. We have that like disintegrate in the GI tract because this is where basically this is going to take place, this first stage. So we also have to have the drugs released, and we also have a situation where it gets dissolved in the GI fluid as well, because it's critical it gets dissolved. So that way we can now start the next phase, which will now be the next phase for the pharmacokinetics.
Can I ask a question before the pharmacokinetic? What affects the dissolution rate at the case of the pharmaceutics? what are the factors that affect the dissolution rate?
The liver, like the metabolism, like if it gets metabolized.
The dissolution itself, before we reach the the particle size, the crystal form, what else?
The
And the dosage form. If it's a liquid, or
yeah.
it's a tablet, how packed is the tablet? Capsules are normally less easy to disintegrate than the tablets. I'm sorry. Yeah, go ahead.
Thank you. So we now look at the next stage, which is the pharmacokinetics. We're basically talking about the movement of the drug down to the body. So we're looking at a system where it starts with absorption. So with absorption, we're looking at it trying across the cell membrane to go down to the blood so that that can be distributed. So that's why we have the acronym ADME. So we look at absorption, we're looking at distribution. We're also looking at metabolism, which would definitely be the effect the liver has. We call it the first pass effect. So after that, we now look at excretion as well as part of the option there. Excretion, when the body tries to get rid of the product as well, waste. So we now look at the ability of the drug to now work on the target receptors. That's talking about the pharmacodynamics. Yeah. So we're looking at the impact because that's actually what we're looking at, the therapeutical effect. Is the drug able to deliver what we are hoping for it to do? We talk about the receptors there, how it gets to the target, how it's going to have like a clinical effect there. Is it going to be toxic? Is it going to have enough dosage for us to be able to have that effect we're wanting? So that's the pharmaceutical effect for it. Pharmacodynamics, sorry. Yes, so that's basically the basis we're looking at. All right.
Okay, a few questions. So let's start with the pharmacodynamic case. Do you think the different pKa values and different pH values can affect the type of interactions between the drug and the receptor? Yes, why is that? Okay, so let's assume that it's soluble enough, it made it to the receptor. Now, if you have a different pH value, or if the drug can have a different pKa value, how can that affect the type of interactions between the drug and the receptor? Well, I mentioned two things, pH and pKa. What effect does these two have on the drug? Ionized and unionized. How does this affect the interactions with the receptor? It can change the induced effect, but why is that? What type of interactions you will see different in the case of ionized versus unionized? Huh? Well, we passed the permeability and solubility. We're talking about how the receptor the drug binds to the receptor. Ionic, thank you so much. So if it's ionized, it can form ionic interaction stronger, right? If it's not, then it could be a hydrogen bond. It could be, mainly hydrogen bond because it would have a hydrogen. Okay, so keep this in mind. Okay, so now let's go back to the case of the absorption. What factors affect the absorption? We already talked about this, but let's just visit them again. What features affect the absorption of the drug? Log P, right? The log P value, the lipophilicity of the drug. What else? Particle size. Okay, so that was actually before when you talked about dissolution. But if you're talking about the molecule size, yes, then the molecule, the ideal molecular weight should be below 500. But what else? So you can think about all the, yes. Together. Okay, this is better, huh? Okay, I'm sorry. So do I need to start all over? Yes? Oh my God. Okay. All right, so back to the pharmacodynamic phase. So we have, how does pH and pKa affect the interaction between the drug and the receptor? Having different pH, different pKa can affect the ionization, right? Now, if the drug is ionized versus unionized, what type of interactions will be affected by that? ionic bond versus hydrogen bond. Okay, if it's ionized, they can form ionic bond. You can imagine stronger interactions if it's stronger. If it's unionized, then you will form hydrogen bond. Get that? So that's the effect at the receptor, drug stage, which is the pharmacodynamic. Now back to the pharmacokinetic. What factors affect the absorption? Log P, of course. We need to have a balance between both of them. What else? Say it again. The drug concentration? Sure. I mean, yes, if you have enough drug to be absorbed, yes. But what are the other factors that can affect how the drug crosses the gut wall? Say it again. Okay, so that's more like distribution. We're still talking at the absorption, okay? So what affects the absorption? Factors affect how the drug is absorbed from the, So lipophilicity and hydrophilicity, which is reflected by log P. Okay, what else? Charge, which has to go with the ionization versus unionization. And ionization percentage is affected by two things, which are pKa, pH. So we already know pKa can affect the drug. How does pH difference can affect drug absorption? Of course, through the same equation. But if you think of the GI, do we have the same pH throughout the GI? Yes. So we have pH different at the stomach and then at the intestine. And as we go, further, it gets more acidic or basic. Are you sure? Basic. Okay. So the pH goes up. Okay. Now, what does that mean when you have the stomach being acidic and basic? For acidic and basic drugs, which ones will be more likely to be absorbed, let's say, in the stomach? Which ones would be more absorbed? Acidic will be absorbed more in the stomach because they will be unionized, right? Basic will be more unionized at higher pHs, right? So they will be more absorbed in the intestine. But there is one more factor that's going to flip this back, which is it has to do with the anatomy of the stomach and the intestine. Surface area. Which one has larger surface area? Intestine. So guess what? Because of the surface area, majority of drugs will be absorbed from the intestine, the small intestine, okay? Because of the surface area. Even the acidic drugs, okay? Even though they are more, unionized in the stomach, but the smaller percentage of the unionized acidic drugs that goes to the intestine will be faster, to be absorbed from the intestine, and that's when the majority of drugs get absorbed. Okay, let's see. Make sure I cover all the points. Okay, before we go to the distribution, I'm sorry to hold you guys. I want to have you have a seat so I could just finish with the rest of the points, and then thank you so much for your help. Okay. You guys get ready for next, for next part, the challenges. But before I finish that, let me cover my points here. So we talked about factors affecting absorption, right? Any questions about that? pH, pKa, lipophilicity or log P, and then the surface area of the intestine. Any questions about that? Questions about anything we have talked about so far? Well, if you get that 100%, can you raise your hand? Okay, excellent. Now let's talk about the distribution. Yes. That's a very good question. So guys, receptors, are they acidic or basic? Is that your question? Yeah, so acidic, are they receptors, are they acidic or basic? Both? Vary, depending on what? It depends, it varies depending on what? Amino acids, exactly. Yes, so remember receptors, they have the drug binds to the surface has amino acids. These amino acids, I'm sure you have studied that in biochemistry, right? What kind of amino acids? You have some are neutral, some are acidic, some are basic. Okay, does that answer your question? So it depends on the receptor. Okay. In fact, you still, when we do drug design, you still want to consider the pH and the ionization and unionization of these amino acids if you really want to measure the interactions, okay? If that's beyond this class. Okay. Questions? Okay, distribution. We have already talked about the blood-brain barrier, placenta, and we will talk about how the drug could be trapped in the GI or in the kidney, okay, in one of these applications. Now, excretion. For a drug to be excreted, does it need to be lipophilic or hydrophilic? Hydrophilic. Why is that? Huh? There's water in the pee, that's right. Because urine is hydrophilic, right? So it needs to dissolve in the urine, right? Okay, but how does the drug become hydrophilic? I mean, metabolism. Thank you, metabolism. Okay. The other thing is excretion. When we talk about excretion, should drug be excreted fastly or slowly? Slowly? Okay. Who says slowly? Raise your hand. Who says fastly? Raise your hand. Okay. What do you guys think? Huh? Balance? That's right. Balance. You should have a balance. Imagine if the drug is fastly eliminated, it's not going to have enough time to stay in the body and produce the effect, right? And at the same time, if the drug is slowly eliminated, it could stay a long time and causes side effects. And you might, or may not necessarily side effects, but you might have longer effects than you want. So the answer is actually you need a balance. Also, it depends what you really want to do. If you need a drug to act the whole day, 24 hours, right? Then you need the drug to stay longer in the body, right? But if you just need the drug to act just like for 6 hours, help you fall asleep and then leave your body so that you're awake in the morning, right? So you want to design the drug in such a way to stay only those 6 hours, right? Make sense? So it depends on what you really need. So, but majority of drugs, you need, a balance. You don't want it to stay too long or too short. Got it? Okay. So what is it about the first pass effect that we always stress out? Why do we care much about? Well, actually, this is in the next part. So the challenges. So guys, ready to share the challenges with us? Come on over. Applause. So team number 12 will share with us the challenges that oral drugs have to face.
My handwriting is really bad. Okay. We said for challenges, we said enzymes, pH, like the stomach acid, and then the potential to be excreted before they reach their target point. We also said that they need to have a balance of hydrophobic, hydrophilic, so they don't get excreted before, and so they can reach their tissues. The effectiveness, toxicity, where it accumulates, maybe in an undesired area, and then just the first pass in the liver, which involves the metabolism.
So what is the pH of the stomach? 1 to 2 to 3, is that an empty stomach or full? Empty. What is the pH of the full stomach? 4 to 7. It depends how full it is, right? For some of us, it could be above 7, so like myself. Anyway, so now you do realize why some drugs are taken on empty stomachs while others are taken on full stomach, right? So if you need a drug to be absorbed and you need the pH of the stomach to be, lower, even though majority of the drugs are absorbed from the intestine, then you still want to take the drug with food, right? Without food in the case of acetic drug, right? But if the drug is basic, which is the majority of drugs, then you want to take them with food because then the pH is higher, then the drug could be absorbed at higher. By the way, food also affects the pH of the duodenum, the first part of the intestine, which the majority of drugs get absorbed there. So keep that in mind. Different pHs affects, I mean, different, after food, before food can affect the pHs, and then it could affect the absorption, okay? Okay, now we also talked about the enzymes. What kind of enzymes? Are you referring to the liver enzymes or the stomach enzymes? Stomach enzymes, pepsids, thank you so much. So the stomach enzymes, guys, are responsible for the degradation of some drugs. In fact, this is why insulin cannot be taken orally. What's the nature of insulin? Protein in nature, right? Insulin is protein. So how does our stomach degrade proteins in the meat? Peptidases, right? And these are the ones responsible for not being able to give insulin orally. In fact, we cannot take any protein as a drug orally. That's why we take them by injection, okay? So if you can design a drug like an insulin to be taken orally, believe it or not, you will take the Nobel Prize, okay? I mean it. So that's a project for some of you. Anyway, so insulin, I mean, with all the advancement in drug design, we're still not able to design something that can be taken orally because, again, it gets degraded by stomach acid and the enzymes mainly. Make sense? Okay, now when you take it orally, what's the other factor that is specific and the major factor when we take things orally? The checkpoint, right? The customs, right? The liver, right? Now, why do drugs have to pass through the liver when they are taken orally? If you think to be metabolized, but if you think of the way our body is designed is to protect us, right? Anything you take orally, the first thing that's going to pass through is the checkpoint, the liver. It will detoxify anything to protect you, right? So think of the first pass effect as something good that protects us from any harm. So you take a drug orally, you eat something, anything you take immediately before it reaches to the circulation, before it even reach anywhere, as soon as it's absorbed, it goes to the checkpoint, the liver. That's why it's called the first pass effect. This is good, but could be bad sometimes when we want to design a drugs. So we should be careful that they can pass this checkpoint and make it. If they don't, they'll be metabolized, they'll be inactivated, okay? Now, what about other routes of administrations? Do they have the first pass effect? No. So first pass effect is specific to the oral drug, okay? So if you take a drug by inhalation, injection, topical, suppositories, anything, they do not go through that. We don't have to worry. In fact, even if you take the drug suppositories, they get absorbed from the large intestine, but they do not go through the liver, okay? Because, the body assumes by the time you get there, then, anything is absorbed has already been metabolized, okay? So it's not gonna go through the liver, that's it. So only those that are absorbed from the small intestine, the stomach, will pass through the liver for checkpoints, okay? Now, I just wanna mention a few other points. So you guys, thank you so much, you did a great job, thank you. Okay, so just a few more points. If a drug can be affected by the acid, then one way to protect it is by using enteric-coated tablets. You've heard of the enteric-coated tablets? So you could actually design it using some enteric coating. We also call them delayed release, such that the drug can pass the stomach, go to the intestine, and get up, released from that tablet out there, okay? And then other forms, as we will see later, is to use something called prodrug, which we will talk about next lecture, which is, basically you design the drug in a way such that it's more lipophilic, but it's not active. And then when it passes that gut wall, then it's converted back to the active form. So it's like a mask used just to help the drug pass through the intestine, and then over there it gets converted to the active form. Make sense? All right. All right. So now to the questions phase before we move to the next application. Questions? Yes. Good question. That's a very good question. The question is, if you looked at the formulations, you'd see that majority of drugs have, the drug and then HCl, right? It's the salt form. And the question is, why do they have this salt? And wouldn't that affect the pH of the stomach? So let me answer the second part. The amount of the drug is not, strong enough to affect the pH of the stomach or the intestine, because if you're talking about, 50 milligrams, and that HCl added to it is not going to affect the pH much. Okay, but the reason they add these is when they design the drug, in order, if they want to be ionized, okay, then they make it in the ionized form, okay, but then they add the HCl to make it salt, such that the drug in the GI can dissolve, because now you have ionized and then Cl minus, so that's positive and negative. So it has to do with designing the drug in the ionized form, okay, to make it more soluble. Now imagine if I do not add the HCl, if I take a drug neutral as it is, and if it's not water soluble, it's not going to be converted into the ionized form, depending on the pH and the pKa. Let's say that we have a drug, and for that drug, it's going to stay in the unionized form. So it's not going to be dissolved in the GI. It's outside the balance of lipophilic hydrophilic, okay? It's too much lipophilic. So in order to solve this problem, we give the drug in the unionized form, okay? I'm sorry, ionized form, okay? Now to give the drug in the ionized form and make it neutral, we have to add something like HCl. So it has to do with the formulation of the drug itself. It has to do with the formulations to make the drug more soluble. I feel like I'm not explaining this very well, just looking at your faces. Okay, so the bottom line is these salts are made to make the drug in the ionized form. Why is that? Because some drugs, they cannot dissolve in the unionized, of course. So we design them in the ionized, and then we add the HCl to, make it form the salt. Now, I should also say that the HCl, as soon as it's dissolved, as soon as the HCl reaches the stomach, it actually dissociates 100%. So the H plus is relieved, and the chloride minus is also released. And so the chloride minus will bind to the drug and help it stay in the ionized form. No, we're talking about solubility, okay? So to simplify it, if you want to administer a drug and make sure it's going to dissolve, would you design it in the ionized or the unionized form? Okay, we all agree it should be in the ionized, okay? How can you force the drug to stay in the ionized form? Make it salt. How do you make it salt? Salt means positive and negative, right? You already have the drug in the mainly positive, because remember, majority of drugs are basic drugs. You already have the drug in the ionized form, it's positively charged. You add Cl minus. This way, it's a salt, it can dissolve better. Is this better explanation? Okay, whenever I get stuck in such an explanation, I rely on you to explain it in your beautiful accent. So for those who this explanation made full sense to them, can you raise your hand so I can pick on you? Nobody's gonna raise their hand, but no. You wanna explain it? No? Are you sure? Yeah, sure. Okay, that's right.
They have to make the drug in a solution initially, right? I know, but like when they produce the drug. Okay, so when companies design a drug, if they want to get in the ionized form, it's obviously going to be in a solution, and for it to be able to dissolve in water, it needs to be a salt. right? Because they're not just going to give the neutral form. So whenever they start to precipitate the drug, they'll add hydrochloric acid in it. So therefore you'll have hydrogen ions and chloride ions. And whenever they precipitate it and make it into a solid, that salt will join with the chloride anions and produce a salt, which can be then put into a powder in a tablet and go into the body. Right?
Thank you so much. Let me see now. Yeah. What's your name?
Kevin.
Kevin. Thank you so much, Kevin. Big applause. Let me see if you got this 100%. Okay. Notice that when I first explained it, I only got few hands. When he explained it, majority of you raised your hands, right? How dare you? You just hurt my feelings. All right. So, I mean, good job. Does it make sense, guys, now? Okay. Perfect question. Thank you so much. Okay, questions? Yes. It's a salt. It's an acid, but it's, well, yeah, it's, you can think of about it as it's an acidic salt. Okay.
To me, a salt will have a positive side and a negative side. So if you're adding HCl to a drug, you're adding a complete compound to it, such that it's not like the drug is not dissociating to HCl and the other component of the drug. For example, if you have maybe a phenol and an HCl attachment, you have a phenol and a chloride attachment.
Okay.
So that the dissociation of the phenol and the chloride give you a phenol as the base and as negative side and the chloride as possible. I mean, sorry, a phenol as positive side and the chloride as negative side. But if you have a phenol and an HCl, it's going to be a phenol and a compound HCl.
Okay.
That compound HCl is probably going to be that divided.
Okay, you're making things hard on me now. No, I like your questions. So, but I'm like, I think, you know, I'm not, you know, I guess, able to answer this part, you know, clearly. So, but we can certainly talk about this afterward. Does it make sense? Okay. Yes.
What he's asking, adding HCl is adding a complete positive and negative, right? Like it in itself is your negative ion and your positive hydrogen. Well, when you put HCl in water, it disassociates at a rate that you can clean concrete with. So at the same time, it'll burn your skin. So but in these terms, you've got some logarithmic disassociation of Cl. So when you actually are adding in an equal amount to this, your ionized form disassociates and hydrochloric acid disassociates, and they bound together to be a salt. Like sodium something and hydrochloric acid are going to be table salt.
Okay. We're going to meet after class, okay?
I mean,
the three of us.
Or was that
Hmm?
wrong?
No.
Oh.
But I think it's, I mean, it makes sense, and we could, you know, we'd want to, like, you know, questions. Do we have a basic salt? Yes. Yeah. You will see some cases where you have, you know, NaOH. Yeah, they might use it in the case of acids. Yeah. Yes, ma'am. Say it again.
It's not as technical as
Okay.
I didn't get what you said about prodrugs.
Oh, prodrugs? Don't worry about it. We will visit them in details with applications. Okay. Okay, let's move to the next application. Let's see. Okay, so the next application talks about the bound drugs. And the best way to talk about it is using this nice figure here. Okay. So for this exercise, guys, think about the effect bound drugs can have on duration of action, the dose of the drug that's administered, drug-drug interaction, and all these factors here. So study this, this page, and try to answer the effect, find the effect on these factors: the volume of distribution, the dose, the duration of action, drug-drug interactions. Okay, and hopefully try to come here at the Dr. Cam, explain to your classmates, how drugs that are bound can actually affect these factors. Make sense? Okay. All right. It's 11:02, which reminds me we might need a break, but you want to take a break now, or do you want to go through this exercise first? Now? Exercise? Good. All right. So that's 5 minutes for this exercise, and we'll discuss, okay? But if you really want to take the break, that's fine. You can go and come back. It's fine. Okay, are you guys ready? Ready? Yes or no? 2 more minutes? Okay, 2 more minutes. Okay, are you ready now? Ready, guys? Okay, let's start with volunteers. Volunteers for this exercise. Any volunteers? You get quiet whenever I ask for volunteers. You want to do it? Sure. Coming in. Applause. Team number 3.
Where that thing? Okay. Okay. So we said like this is way too high. Like how the drug, if it binds to macromolecule, what effect will it have? So the drug gets to the cell by the cell pores through it, and once it binds to the plasma protein, it cannot get out first. So you will have like two types of drugs, ones that are bound and ones that are unbound, and that will have an effect. Like the ones that are unbound will take longer for them to reach their target. And then it will also have an effect on the volume distribution. You will need, I think we said we have to have a higher volume distribution to reach this target, as well as the dose administration has to be higher because you have some that are unbounded. And is that right?
Yeah.
Right. Okay.
So as far as the dose, those drugs that are bound to these macromolecules. As far as the dose, drugs that are bound to these macromolecules, albumin, red blood cell, or fatty tissues, would you need to give them at higher dosage or lower dosages? Higher. Everybody agrees it's higher? Because you need to counteract the amount of the drug that's actually binding to these macromolecules. Now remember, only drugs that are free are the ones that are able to reach the receptor and produce the pharmacological effect. Those that are bound to the macromolecules are stuck in there and they cannot exert any pharmacological action, okay? So because of that, we give higher dose of the drug, okay? Now, what about the duration of action? Would these drugs that are bound to these macromolecules have longer duration of action or shorter? Longer, everybody agree it's longer? Why is that?
Yeah,
they stay in the blood longer, and as the free drug is being eliminated, now these drugs that are bound will be released. Exactly. So they will supply the plasma with more of the drug, so then the drug will stay longer. Notice here that we are talking about the duration of action due to the distribution, not the duration of action due to binding to the receptor. Remember in earlier class, we talked about the duration of action, how long the drug binds to the receptor. Now that's one factor. The other factor, which is distribution, how the drug stays in the blood, actually has higher impact. This is the one, the duration of action because of distribution. This is the one that mostly affects how long the drug affects, how long the drug will have its pharmacologic effect. Okay, so this is more important than at the receptor level. Okay, let's see. We talked about dose, duration, action. Volume of distribution, which one will have higher volume of distribution?
So we'll have to have higher volume distribution just because they're binding like different things, one in the free and then the unbound one. So we'll need to have a higher.
Excellent. So the volume of distribution for the drugs that are bound, they will have higher volume distribution. Now I want you to think about something, if one person has a certain amount of water, or let's say volume of the liquid in that person, how could you have different volumes for two different drugs? Let's say one drug is bound to these macromolecules, another one does not. Yet one of them will have higher volume distribution, but it's the same person, right? It's the same body. How could you have two different volume distributions? So the amount of that, that's a good point, amount of protein in the blood, but let's say we are talking about the same person. Let's say that I'm the one who's taking the drug, right? So apparently I have the same volume of distribution, right? I have constant volume of distribution, which means I have constant volume of fluids, okay? which is like 42 liters, I think, something like that. So how can I have, but if I take drug X versus drug Y, for drug X, because it binds to these macromolecules, it will have larger volume of distribution, while drug Y will have smaller volume of distribution. How is that possible when I'm the same person and I have the same 42 liters? I mean, they do bind to the fatty acids and albumin, but that's why we have something called the apparent volume of distribution. So there is the true actual volume of distribution, and there is the apparent. So keep that in mind. We will talk about this when we visit the pharmacokinetics, how the drug, okay, just keep that in mind. Think about it, and it's in the notes as well. So the last thing is the drug interactions. Now, how do these drugs that bind to this tissue get affected by, like, I guess, how this fact about these drugs can, you know, impact drug-drug interactions?
The unbind are more than what's supposed to be, then it's going to be toxic at the end. When it, like, if you have way more than what's supposed to be given, then those unbonded will turn out to be toxic to the blood.
Okay, that's true, but it has, but this is in terms of toxicity. This does not explain drug-drug interactions. I will explain to you guys, but what she's referring to is, you know, when you go to a surgery, they ask you if you ever had anesthetic drug before. They always ask you this question, and they always tell you there's a risk that anybody who goes to a surgery, they might actually go into a coma or a death, right? Why is that? These drugs are lipophilic. They bind to the fatty tissues, right? And there is no way to tell how much fat is in one person. It's hard to predict. So they assume that, okay, these drugs bind to the fatty tissues, we should give higher dose, right? So they do the math, they give enough, you know, hopefully enough or the right dose for that person. But sometimes for one person different than another, they might have more or less fatty tissues. Let's say they have less fatty tissues. So we give higher dose, and then this dose stays in the blood instead of binding to these fatty tissues. So then what happens? Toxicity. So this person can go into coma and death because of the anesthesia, right? Make sense, guys? Okay, so I will answer the drug-drug interactions question unless you guys want to add. Do you know, does anybody, you want to?
So when a drug has a higher affinity to a plasma protein, and given with another drug that has affinity for that plasma protein, the higher affinity will displace it and cause the free protein of the weaker bound to go up, and that'll cause toxicity.
Thank you so much. Thank you, guys. Okay, so to repeat what Kevin just said, this here shows two drugs. This effect here shows, first of all, in the first graph, we have one drug that binds to the plasma protein. And this applies not only to plasma proteins. Anytime we talk about a drug that binds to these macromolecules, the major ones are albumin, plasma protein, fatty tissues, and some cases red blood cells, okay? So let's talk about albumin because it's the most common. We have a drug bound to the plasma protein, okay? Everything is normal. Now, if we take another drug that also binds to plasma protein, it will compete with it. So now the other drug will be released. Also, the first drug will not have enough, places to bind to. So both will compete for the plasma proteins. So their free amount in the plasma will be higher. So you will have higher, toxic effect from both drugs. So this is one form of drug-drug interactions. Okay, there are different forms of drug interactions, but this is one of them. Okay, now let's open the door for questions. John. Remember when we said that if the drug binds with a strong affinity to the receptor, it will have a longer duration of action? Okay, so this is at the level of the receptor. Now this actually have a lower impact on the duration of action of the drug. When we say a drug is taken every 6 hours, we really referring to how much the drug stays in the blood and how is it excreted. We're not looking at the receptor, right? Okay. The only time this factor where the drug is bound to receptor is an issue is if it's irreversibly bound to the receptor and forming covalent bond, then this becomes the predominant effect. Because guess what? Once the drug binds to the receptor, it's there forever. And even though the drug is out of the body, let's say that you wait a few hours to let the drug completely out of the body, you still have those that are bound to the receptor, inhibiting it or activating it forever, or and that will be the predominant effect. We will go through cases like that. So I know you have a question. Yes, ma'am. So the question is, if we have an obese patient, does that make them at a higher risk of getting, intoxicated in case they want to go into a surgery? Honestly, I'm not sure. I'm not sure if that would, make the calculations more difficult. But I know that doing the math to find the dose is, is difficult, and that's what causes. I mean, not the math itself, but trying to predict, how much drug you should give does not always give you the right amount. That's why there's a risk that you might think this is how much I should give, but for one person, they might have more. I mean, for toxicity to occur, they might have less fatty tissues, and that's such that the drug actually is not binding to these fatty tissues. If the drug is staying in the plasma and causing the toxicity. But that's a good question. So now, whether for obese, you will learn about special populations later on, and how drugs should be dosed for geriatrics, pediatrics, and all these special cases. Okay, so, but I mean, that's a good question. I'm sorry I couldn't answer it though. Okay, all right. Yes, ma'am. Say it again. Oh, go ahead. Yeah.
So when you have an obese patient, when you have an obese patient, it makes the actual calculations more complicated because that anesthetic is taken up by the fatty tissue. So you have to be really careful because they do need more anesthesia because they have so many more fat cells. But the problem is that when you take them off anesthesia, you sometimes have a very hard time waking them up because it has accumulated in that fatty tissue. So that's one of the big risks associated with that.
Excellent. Thank you so much, Molly. In fact, this explains the duration of action, why these drugs have longer duration of actions, because again, the drug is being released slowly. Even though it's eliminated out of the plasma, those that are bound are now going back into the plasma, and then you'll have a longer effect, okay? Perfect. All right, more questions. Are plasma proteins positively charged or negatively charged? Huh? Plasma proteins, are they positively charged or negatively charged? Albumin is positive, thank you. Well, first of all, as we know, proteins have amino acids, so the right answer would be it depends on the amino acids. And guess what? Albumin has more positively charged, amino acids, which is why. Which drugs do you think will bind more to the albumin, acidic or basic? Think of both. The acidic, in the case of it's ionized or unionized. Of course, it's unionized, then we don't care. But when the drug is ionized, which one will have the perfect charge to bind to the albumin? Acidic. Okay. Luckily, most of the drugs are basics, like we said, but those drugs that are acidic, they are more likely to bind to the plasma protein than other drugs and more likely to cause these side effects, okay? Get that? Okay. Now, for those drugs that bind to the fatty tissues, which ones will be more likely to bind? Of course, ones with high log P or low log P. High log P, okay? Everybody get that? So with those that are more lipophilic, they are more likely to bind to this tissue, okay? Now, we also mentioned that for a drug to be excreted or eliminated, it should have a balance. It should stay long enough, but not, you know, not too long, and stay just the right amount of time. If we have a drug that does not stay long enough, how can we increase its duration of action? Should we, let me just, I guess the phrase, and if a drug has short duration of action and we want to increase its duration of action, would you make it more lipophilic or hydrophilic? Lipophilic, why? Exactly, so that they can bind to these fatty tissues and then get released later. In fact, this is a technique that we use a lot, and we will see, which is anytime we have a drug that is, you know, does not have enough long enough duration of action, we make it more lipophilic such that it stays longer in the body. Okay. Questions? All right. If you got everything we talked about so far, raise your hand. Okay, good. So I don't have to ask Kevin to explain it. Okay, so next exercise should be straightforward. In fact, I'm just gonna show the answer immediately, okay? It talks about Lipinski's rule. So look at this drug. How many rotatable bonds does it have? 1, 2, 3, 4. Basically, all the single bonds are rotatable, right? 1, 2, 3, 4, 5, 6, 7, 8. Do we count these in the circle, in the part of the, no? And the fluorine is 9. So how many rotatable? 9. Notice we have not counted these in the ring because they cannot rotate. So 9 is below 10, so check, number 1. And then how many hydrogen bond donor? Any hydrogen bond donor here? No. How many hydrogen bond acceptor? 1, 2, 3, 4. Okay. Molecular weight, 325, below 500, and log P, 3.5. So do you expect this to be a good example of a drug that could be taken orally? Yes. Got it? Now, there are exceptions for Lipinski rule, but you know, this is the general, in the general case, that's what we, that's the rule we use, okay? Any questions about this? And you do not have to memorize the Lipinski rule, just be able to use it. Okay, next one. Empirical. Yes, ma'am. Oh, somebody has a question. Yes. The volume distribution for the previous question in general. So why one person with the same volume like myself have a 42 liter can have 2 different volumes for 2 different drugs? Okay, sure. Exercise number 3. Okay, so back to exercise number 3. What's Lipinski's rule? There was like number of hydrogen bond donor, number of hydrogen bond acceptor, number of rotatable bonds, molecular weight, and log P. Molecular weight is below 500, log P below 5. The number of hydrogen bond donor acceptor is, I'm sorry, the acceptor 1, 2, 3, 4, that's below 5. Donor is 0, that's below 10. Number of single bonds, 1, 2, 3, 4, 5, 6, 7, 8, that's below 10. So this is, will follow Lipinski's rule. Okay? So back to the volume of distribution. There is the actual or real volume of distribution, and there is the apparent volume of distribution. Now, how is the volume of distribution measured? I'll give you a hint, okay? So if I want to measure the volume of distribution, I mean, not the actual, you will figure out, you will find out what I mean. So I'll take a drug and wait until it's completely distributed into my body. And then I'll take a sample, measure the concentration of the drug, okay? And since I know the dose, because I gave that, I took the tablet, and I know the concentration, can I get the volume? Right? The math, concentration equal dose over volume, right? So if I have the concentration of the drug, because I took a sample out from my blood, I measured the concentration, and I know the dose of the drug that I took, okay? And let's not take orally, because orally might be part of the drug absorbed, other part is not, so I'm not sure about the dose. Let's take I took an IV injection of a dose. Let's say I took like 5 milligrams of a drug, and then I waited for like a few minutes. Now I took a sample and measured the concentration. So now I have the concentration, the dose. Can I do calculate the volume? Yes, so that's for drug X, okay? Now I do the same experiment, but with drug Y. And let's say that Y is bound to these large molecules. And I take the sample. Now, when I take the sample and measure the concentration, which concentration of drug am I measuring? Is it the one in the plasma or the one in both plasma and the ones that are bound to the protein? Guess what? Only in the plasma, okay? So I only look at the concentration of drug that's dissolved in this fluid. I cannot measure the concentration of the drug that's bound to these red blood cells or proteins. So I think now we are getting to the point, why do we call it apparent volume distribution? Because those drugs that are bound to the tissue, when I take the same, a dose of that drug that bind to the tissue, a lot of the drug will be bound to these macromolecules, albumin, whatever, and only few percentage will be in the blood, in the plasma. So I take the sample and measure the concentration, and I will see a small concentration. When I do the math, I decide, okay, so this is the concentration, that's the dose I took. I calculate the volume. Guess what? What volume do I get? Is it high or low volume? High volume. Because concentration equals drug over volume. So volume would be equal dose over concentration. The dose is fixed. The concentration itself will vary from one drug to another. Those that are bound will have low or high concentration. Low. So then it's going to appear that the volume is higher. So those lipophilic drugs can have a volume distribution, let's say 100 liters, right? While in fact, I only have 42 liters in my body. So what's going on? Well, part of the drug is not really showing in the plasma. So why are we doing this? Because eventually we only care about the concentration for the drug that is free in the plasma, not the drug that is bound. This is the one that binds to the receptors. When we give a dose, if a drug has a volume of distribution, higher than another, I'm going to use that volume of distribution to measure the concentration, to calculate how much dose I'm going to give to the patient. I know it's too many information, but Kevin started, not me, okay? I wanted to explain this later on, but maybe we'll have an application on that to just, get a better idea. We'll have an example where you have two drugs and ask you to measure the volume distribution, then you will see that more practical, okay? So if you get that, good. If not, it's okay, we'll visit it again because I don't want to be running out of time. Are you trying to make me lose the class today as well? No, okay. Okay, but that's a good question. All right, so any questions except, about the volume of distribution? Because we will visit that. Any questions so far? Okay, so let's go through the empirical method. So as far as the empirical method, I hope you guys get the point, which is anything that is not a carbon is a function group that has some ability to solubilize the molecule, and it will solubilize some number of carbons, okay? So do not memorize which groups or what's the solubilizing potential for each group. These will be provided. And I know you hate organic chemistry, I do the same. So we're not gonna memorize the groups, which one is amide, which is amine. So I'll provide you with circles of the group and say, this is an amine, and it has on the table the solubilizing potential, all you have to do is just do the math, okay? Because I know you're probably not gonna need to memorize what function, the names of function groups. With time, you will catch up on these names, but if you don't, that's fine. So in this drug, we have an amide here. What's the solubilizing potential for the amide? 2 to 3, right? So how many amide we have actually? 1, 2. So let's see 2 times 2 to 3, okay? And then we have how many amine? 1, 2, 3. So 3 times, what's the solubilizing potential for the amine? 3 carbons, okay? And we have 1 ether, which is here. Solubilizing potential for ether is 2. So that would be, let's say, 2, 9, 4, 2, 6. So that's 11, 15 to 17. How many carbons do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. 23 carbons. Okay. So the drug is able to solubilize this number of carbons. What about the other ones? It's not able to solubilizing them. So would that be URL soluble or not? Not. So it'd be insoluble. And by the way, this is just a rough. This is just a rough prediction of how the drug could be water soluble or not. So this will help you. If you do not know the log p value, you could use this method to see if the drug will be lipophilic or hydrophilic, okay? Also, notice that we're not even looking if the drug is ionized or unionized. Now, at some pHs, this drug might be ionized. When it's ionized, guess what? One ion is able to solubilize 20 to 30 carbons, believe it or not. So if one of these groups is ionized, then the drug becomes immediately soluble. Right, I'm sure you have lots of questions about this. Yes, sir. Okay, okay. So in the notes here, we talked about the empirical method, okay? And it was telling us that each group is able to solubilize a number of carbon atoms. So this group, for example, alcohol, phenol, is able to solubilize 3 to 4 carbons. Amide would solubilize 2 to 3 carbons. So, and so forth. So if you know what function group it is, then you will be able to know how many carbons it can solubilize. So now you have a molecule. It has carbons and it has other non-carbons. These non-carbons have ability to help solubilize the other carbons. So if I have enough of these groups, function groups that have solubilizing potential, they can solubilize the other carbons, the drug become water soluble. If you have more carbons, the drug is insoluble, okay? Right, more questions. Sorry, you had to see this. Anyway, okay, so, yes, ma'am. Okay, so, no memorization, remember? So you will be given a table that shows each group and its solubilizing potential, okay? And not only that, but I know that you probably forgot your organic chemistry and which groups is an amide, which is amine, which is carboxylic, which is, so you will see circles like this example here that shows, this is an ester. It's gonna tell you this is an ester, this is an ether, this is an amine, and you just look up the number and then do the math. Can't be easier, can it? Huh? Yes, yeah, the numbers, the solubilizing potential is given. Question? Yes, sir. Say it again. Oh, that's a good one. Okay, so guy, the question is, this carbon here is part of the group, right? Do I count it? Yes, you do, okay? So in the case of our example here, we have carbon here that's part of the amide. Do we count this? Yes, because the rule says you count the number of carbons in the molecule, all the carbons. It does not say excluding those that have been already part of the, okay? Now notice that the potential says from 2 to 3 or 3 to 4, because this is it's called empirical. This is just an approximate way of getting an idea of whether the drug will be soluble or not. Okay, so I just want you to get the feeling of how can you tell if a drug could be water soluble or not, just by comparing between how many atoms are carbons, how many are not. In fact, there is another way that simply says just count the number of carbons, number of non-carbons, compare between them, and then see which one has there's higher. I think there's a range between these two, but this is like even simpler way. But I like to make things complicated. So anyway, questions. Say it again. Sure. After you mean, or now? Okay, well, let's do this actually. Start working on the last exercise. So just make sure we don't run out of time. Start working on the last exercise. In the meantime, if you have questions about anything, ask me, okay? So in the last exercise, it says that a truck driver wants to take an antihistamine. As you know, antihistamine causes drowsiness. So he wants to stay awake because he does not want to drive when he's sleepy. And then we have two antihistamine, number 1, number 2, and then you're going to recommend one of them to help him stay up and alert. So both have a pKa value of 6.4. The pH is 7.4, okay? So you could use the Henderson-Hasselbalch equation, or you could just go with the short table to find which one would be ionized and unionized at the plasma pH. And then the information you're going to use is that the histamine receptors in the brain are the ones that causes people to fall asleep and be drowsy. Your goal is to pick the one that is not able to cross the blood-brain barrier and cause the sedation effect, okay? You got it? Okay, John, you have a question.
The specificity
Okay, guys. So that should be a straightforward application, right? So which one would you recommend for the truck driver? 2. Why? Yeah, number 2. That's right. Why is that? Is it acidic or basic? It's acidic. And if you do the math, or if you use the table, you have pKa, pH. This one would be ionized. This one would be unionized. Okay? So this antihistamine will not cause drowsiness. Now, you could check the structures for the, have you heard of the first generation, second generation antihistamine yet? I mean, I know this is your first, pharmacology class ever, but as you work at the pharmacy, have you heard of that? Okay. So I actually named this number 1 on purpose because this is what first generation looks like. This is what second generation looks like. Second generation will not cause a drowsiness because of the fact that they are acidic, they are ionized at pH of 7.4, they do not cross the blood-brain barrier, and they do not cause drowsiness. Okay? So all these Zyrtec, Claritin, fexofenadine, or Allegra, what else? All these are second generation. So what would be example of the first generation? Benadryl. Benadryl causes drowsiness. Now let's flip this application and say, someone comes to you and say they need something to help them fall asleep. Which one would you choose? First generation. But guess what? These antihistamine are the worst option you can ever give for someone who wants to sleep. Do you know why? Huh? Oh, okay, so she says that's a good point. So the body gets addicted to it, desensitized. I mean, sensitization and all these tolerance, so you have to increase the dose. But there is another reason for it. Say it again. Say. They will reach the brain and cause the drowsiness, but the reason they are not really a good option because they have a long duration of action. You take Benadryl, and it has like 18 hours of duration of action, which means you're gonna fall asleep and then you're gonna wake up the next day in the morning, you're still drowsy, like for 18 hours from the time you take the pill. It's horrible, okay? So you only take it like, maybe for a few days for an exception. But the ideal drugs are prescription drugs. They're not over the counter, and they have perfect duration of action, 6 hours. Boom, you fall asleep for 6 hours, and then you wake up fresh and energetic and everything. Okay? So we will go back to these antihistamine and the sleeping medications, talk about this again. But for now, we just wanted to point this out. Let's see, I have a few comments here. Okay, the same thing apply if we say which one is safer in the case of a pregnant woman. You know the answer. Okay. Okay, we missed. Okay, we wanted to talk about which one would be trapped in the urine. Okay, so let's talk about this in the hopefully last 5 minutes. We did not give you a break today, did we? I mean, enough break. Okay. So the idea of a drug being trapped in general, whether it's a urine or intestine, is you have 2 different environments that have 2 different pH values, okay? So when the drug is in one pH value, it will have a different ionization and ionization. So in one case, because of the different pH, they are able to cross the membrane because they are unionized. And then when they come to a different pH, guess what? They become ionized, right? So they are not able to go back. An example of this is how the drug is excreted in the urine. Urine, is it acidic or basic? Acidic, okay. I'm glad everybody knows that. Now remember, this can change depending on the food you take. You might make it, less or more acidic. That's why cranberry juice, if you take it, you could actually increase the acidity of the urine and help elimination of the basic drugs. Anyway, so drugs will pass from pH of 7.4 to 6, the urine. When they are in the plasma, at 7.4, they are unionized. they pass the kidney tubules to the urine. They get to the acidic environment, they get ionized. They are not able to go back. So they are trapped in there. More of the drug is being, going into the urine, trapped and excreted. Okay? On the other hand, if you're talking about the GI and the blood, again, GI, the stomach is acidic, the plasma is 7.4. So then the drug, the basic drugs now move to, hold on, the acidic or the basic? Acidic. Acid drugs, they pass the intestine or the stomach to the blood. They get ionized, they are trapped, they cannot go back. So the idea of trapping basically says you have two different pHs. Because of that, the ionization percentages changes, and that's how drugs get trapped. Okay, so think about the example here and try to see which one would be trapped in an acidic urine. Okay. Questions? We have 2 minutes. Okay, well, here is the thing. So for next lecture, so for this week, we're going to continue working on these 38 pages, okay? So for next lecture, we're going to have a rat that covers, let's say, metabolism up to excretion. So I will send you the number of pages. How's that? Okay, so I'll send you the number of pages for the rat. It will be an overlap because you've noticed we have not talked about metabolism at all, right? So we'll talk about metabolism, and then on Friday, we'll talk about the remainder of the topic. So I will, send you the number of pages for each rat on Wednesday and Friday. Okay, you guys have a good day, and I'll see you in shortly, actually. Guys, make sure you give me the sign-on sheet with any feedback. Okay, thank you.